Welcome back, everyone. In today's video, we're going to explore something a little bit different. I have an article from Gaber about how to accumulate transforms. The idea is that instead of creating like local matrices and world matrices and then combined and multiplying them from parent to child, the idea is that you don't do matrices at all, and you combine your scale, your position, and your rotation from parent to child. So you can have your local transform and your world transform. And then you take your world transform, and then at the very end, you make your matrix. So this way, you're only doing one matrix creation, and you're actually doing no matrix math at all, which is probably more math intensive than doing it this way. So we're going to try this out, and it works well, but we're going to take it one step further, where in his example, like he mentions that this is how Unreal Engine works, is that it does this with the transform and then creates a matrix and then passes the matrix to the shader. We're going to take it, like I said, one step further, and we're not going to pass a matrix to the shader. We're just going to pass the world rotation, scale, and position, and then apply that to our vertices. So this way it becomes like a pure transform, no matrices really at all. You're still going to use your matrices for the view space, and you definitely need a matrix for projection. So you can't get away from matrices altogether, but you can have one matrix less if you really want to, and it works out. I managed to actually get it working. So yeah, we're gonna take this like we're gonna do this. This is fun. Like, it's a nice exercise, and it's going to be the new direction I'm going to be doing it, and I apply this all in ECS, so you can see how this works in ECS as well. So we're going to get first. I'm going to basically say this is going to give us a new direction for fungi a little bit, because I'm not going to do pure transforms, but I am going to use the overall most of it because it works really well. Like, I've been playing around for a couple of weeks now, and I like it. I prefer it this way than dealing with a bunch of matrices. So thank you, Gaber, for the inspiration. So here's my transform component. And as you might not notice that certain things have changed. Like, I'm commenting out sections of code. And originally I had some of these set up as with underscores underneath it. The reason I had a reason for it is because I was still trying to live both in the functional and an object-oriented way. That's why I had these functions called position, and these would then change the modify state and then update the position for me. I decided to just go kind of all functional on this, because in the end, it's just easier to just modify and then always remember the set is modified, because I have so many sections in the area in fungi now that's working more functional, and it just, like I said, it just makes more sense just to kind of go all in. So that's kind of one big change, is a transform has changed. So I had to really go back and really fix a lot of my code, because sometimes I would actually access these directly, but I had to use the underscore. Ooh, whoa. Screen went black and came back, but that was a big lightning bolt. Oh boy. Let's see if I can record this during a lightning storm. Okay, so transform changed. And before, when I used to do parenting, I had an object called hierarchy. All it is kind of extended transform with a hierarchy, and didn't really do too much other than that. The only thing it would do is that it would actually modify the model matrix and make it a world matrix, which works for the most part. But I think sometimes I wanted access to a local matrix, and I didn't have it. So I'm replacing hierarchy with something called transform node. And transform node is the exact same thing. The only difference is it contains scale, position, and rotation. And this will become the world position and scale and rotation. So this way, transform will always have my local, and transform node will always have my world. But everything else, when it comes to how the hierarchy works, is here. It's still add child and remove child. I don't think how it functions is the same. I had other functions here like get world position, get world rotation, which I kind of don't need anymore because my world rotation kind of exists anyway. So as long as I process through everything, everything's already there. So yeah, that's transform. And like I said, how the whole parenting still works the exact same way. So like I said, there's not much hasn't changed. Like I said, the only difference is this one now contains more data, which will hold our world position information. And basically the big change is really update node, and it really just follows the same idea of how Gaber did it. I was never sure how the relationship, because I know I tried to do this like 2 years ago when I first started graphics programming. I was trying to see if I can do this without matrices, and at the time I just didn't know the order of operations very well. So this one kind of lays it out really well. 2 years later, it's like, oh yeah, this makes perfect sense. Duh, I'm an idiot. I was an idiot 2 years ago, but yeah, in time you'll learn. So like I said, it's pretty simple. If you just want to go from parent to child when it comes to scale and rotation, all you need to do is just multiply. Parent multiplies child. That's it. It just keeps going. The only tricky thing is position. Position changes based on its parent. So if the parent has a scale, a rotation, and a position, all that has to apply to the parent position. So that's actually the trickiest part, which I think I might have had problems 2 years ago. I didn't know how to do this correctly. The magic sauce is that you scale your local position by your parent scale. That's it. You scale it. First you apply the scale. Then you apply your parent's rotation to that scaled value. And then when it's all done scaling and rotating, then you add your parent's position to that. And when you're all said and done, that becomes your new world position. I have CN for child node and PN is for parent node. And if there's no parent, local and child, local and world is the exact same values. So it becomes a very simple way to kind of just update a node. So here's a node. I know what my parent is, and I'm just going to do it. Done deal. And that's it. Very simple, not too complicated. Works out. The transform system has, I don't think, changed too much. I still create a matrix because I still have a lot of code that uses matrices, and I might still just use matrices for the most part. But at the same time, I'm like I said, this is gonna do both for a while, and just to play around with it. So yeah, the transform system works the same. It just creates a transform, and just call it a day. I just probably tweaked it a little bit. That's it. Then we have our transform node system, and the transform node system runs before. Let's see, T model. Yeah, this just creates our local matrix, which is a problem because if I need my world matrix values, like for parenting, this won't work. This is mostly here, really, like as I said, for things that before I start implementing like this pure transform type of thing, because the camera still works this way, and I don't want to change the camera because I still need to view matrix. So it's just easier just to do it that way. So this is mainly here, really just mostly for the camera, but I probably will continue doing this, but so whatever. Does this do it? Don't think it does. So here's the transform node system. It's pretty simple. All it does is loop through every single entity that has a transform node and a transform, and yeah, it follows a lot of the same code as the hierarchy system. So there's not really much to teach you. It's a lot of the same code. I just changed it up a little bit. So instead of dealing with matrices, I'm just dealing with transforms. So it just looks a little longer because now I have to do scale, rotation, and everything else. And like I said, it's the exact same thing as I have that update function. And you might say, why am I not using the update function? The only reason why I'm not using the update function is because I create a v value. So so I don't want, if I have like tons and tons of nodes, I don't want to I don't want to create a bunch of memory for it. So I think in future iterations, because this is actually my first iteration, I think in future iterations, I figured out a way where I can actually use the update function and not create this extra v value. I can't remember now, but it'll be in future videos, I guess. System changed up, but for now, like that's why I'm doing this. I'm doing it because I'm just trying to avoid creating this v value multiple times. I create it once and I reuse it, so this way I'm using up less memory per frame. That's the whole point of it. But like I said, I think I found a way to do it without creating that extra v, just by using, I think, CN position. I think that's how I did it. I think I used the CN position. Because I think one day I had a eureka moment where I can just, instead of here, I can do something like this. So you know what? I'll just show you now because I think I remember how I did it. So I guess to simplify this, and I guess to avoid having all this extra crap right here that you actually don't really need if you make a function work really pretty well. So I did scale multiply, and then I save it to my node position, if I remember correctly. So now the value is stored in there and not stored in V. Then I pass in my node position as the output. So that position gets rotated and it returns back CN position. And then all I have to do is add parent position. And you know what, to prove my point, just to prove it works. Well, you know, I can leave it here. It's no big deal. I'll just comment this out. And I'll just put it into system. Do I use the exact same code? I think I do. Why not? Let's try it out. See if I broke this. Oh, it works. There you go. I remembered. I remembered how I fixed it in the future. So yeah. So like with this small change, like that I did right now, like I said, this is something I already did before, just recently, probably like 2 days ago. I can get rid of the v, so I don't need this v variable anymore, and that means I can really just dump all this, comment it out, and just call the update function. Again, I still probably will. I think I still kept it there simply because here I'm still creating a CN value, a CN variable, a CT variable. So I'm still creating extra variables for every loop. So in the end of the, like, even though I did this change, that means I have one less variable I'm dealing with. I still probably better off leaving it this way because this set of variables is only happening once, and I'm not calling a function. Let's say if I have 1,000 entities, I'm not calling a function 1,000 times. I'm just doing a loop, and I'm not doing the extra function call. So it's like 1,000 function calls less, and out of those 1,000 function calls, there's less variables being created and allocated. So it's really like a performance thing, really. And when you're dealing with, especially when you're dealing with entities and you're updating the entities, you really need to optimize it. So like I said, I've managed to, it can optimize it a little step further because there's one less variable I'm dealing with by just reusing the n variable. Like the n variable is going to have the data copied into it. Might as well just use that as the starting point. Just start putting it in there and start using it. Yeah, and that's transform node, like I said, nothing has changed. It's just doing a lot of the same and things like that. Trying to think, there's something else. All right, so that's transform. So So now we know how the transform works. We're just combining our scaled rotation and position from parent to child, The last step is, now that we have all these things calculated, how do we get it to the shader? So one simple solution for me to save a lot of time is I just create a UBO. I'm just calling it the UBO world because I don't know what to call it, because I'd rather call it the UBO model, but I'm trying to keep this here for a while. So in the future, I might end up getting rid of this one and replacing it and calling it this. Maybe I'll just have it all combined into one. Like I can keep the matrix if I want in the normal matrix, but add these to it. I don't know. I'm not exactly sure how I want to go about it. Since I fixed UBOs to do one single call, so I can do like 20 variables and do one call straight to the GPU. So no big deal. And this is for the future, for the next video. So you can ignore that. So like I said, one simple way is just to create a UBO that I can easily update and pass into information. And I think one last big change I totally forgot is the render system. So when I'm rendering, you got to be able to pass it to the shader as well. So in my load entity function inside my render system, so I kind of marked it with the to-do to remind me to come back here and confirm if I want to keep this or not. But I check to see, if node and transform node exists. If no transform nodes exist, I use that. If not, I use transform. So this way, it's kind of like backwards compatible. Or if I'm not using hierarchy, I can just use transform in its place. And that's kind of one of the reasons why I needed transform to get rid of the underscore. So so transform node and transform are equal in terms of property names. So so transform node and transform can be kind of interchangeable. So I can use rotation and scale properties the same. So it makes this code a lot easier. Before I had an if statement and I was going back and forth between the unscored versions. So that fixes that. So like I said, all you have to do is upload all the information to our UBO. And then once we have it in our local binary, we upload it to the GPU and done. So now the GPU has the UBO updated with the new transform information. And once you have it up there in the UBO, then you just go into the shader. So with a shader, like I said, I'm importing a new UBO, which all it does is take the UBO pointer and just says, okay, use it for the shader. Here's our UBO, and I'm giving it a name because I want to use rotation, position, and scale. And if I were to not give it a name, these will be the global names. So now, for me to access these values, I have to say model.rotation. So this is something different I'm doing that you haven't seen me do before. Ideally, it's probably actually best idea that you actually do that for your but I kind of like just keeping them simple, so I can just access. I just make sure these are well named, so I don't actually create scripts that can screw up. That's why I did this, because rotation, position, it's just a simple names, it's just generic names that I can probably accidentally use them as variable names. So now we have all this stuff in the shader. We got the information in the shader. How do we apply it? So originally we did this right here, this line. We did our projection view matrix, which is our view matrix and a projection matrix merged together on a CPU and then uploaded. I did that in previous videos, a couple videos ago, as an optimization. So this way we would have one less matrix to deal with. And we multiplied by our model matrix, and we multiplied by our position. So since we're getting rid of, or we're trying to replace model matrix, we have to do it ourselves. So the first thing is we need this function. This is a function we had for a very long time, how to apply a Quaternion rotation to a vector. So it's very simple. I give it a new name and I fixed it up. I try to make it as small and as optimized as possible. So it's easier to kind of just keep it inside the script, inside the shader. And all you have to do is pass in the Quaternion, you pass in the vector, and you're done. So, like I said, the first thing you need to do, you take your position and you scale it. That's always the first thing. You scale it first. So you scale the position. Then that scaled position goes into the function, which then does the rotation. And then when it's all said and done with the rotation, it returns back a vector 3 of its new rotated position. And then you add the actual position from the for your model. And that which is basically your world position, which is your parent position plus your local position. So once you have pose, you can just multiply it by your projection view matrix, and you're done. And that's it. And that's pretty much the whole workflow of a pure transform. You can actually go from there to you can use all your code, do all the work, the whole pipeline, and then bring it all into the shader and still apply it. Like I said, this is the secret sauce to do it. Like you need some way to multiply Quaternions in vectors. I really hope at some point shader language, GLSL or HLSL, like Microsoft's DirectX stuff, I hope they someday bring in Quaternion math, so this way you don't need. So this becomes super much easier. If you can get like Quaternion and dual Quaternion mathematics like brought into the shader language, it'd be really awesome if it's built into it. So this way you don't have to compile it, you don't have to always keep it in your scripts. So that's the only thing I don't like about this, is because I have to do this. And it's not too bad. It's just 2 extra lines of code that replaces a model matrix. I think generically for a lot of things, it might just be easier just to do a model matrix. Like I said, it's easier because you don't have to have this function in here. You don't need to do this. You'll have two less lines of code. I'm not exactly sure if model matrix is faster, like compared to doing it this way, because because you do have 2 cross products, but cross product, there's a lot of, for every cross product there's quite a bit of multiplication and addition, and so it is during a model matrix. It just depends on how you have to count how many addition and multiplication operations are done, and if, let's say, this approach actually has less, then it might be more efficient to go this route. You might squeeze out a little bit extra performance just by having a few less multiplications and things. And if you're not dealing with any scaling at all, you can always take this scale out, and this way you're doing less multiplication on top of that. So, like I said, and another cool thing I like about this, even though I might still go back and just use my model matrix just for simplicity's sake, this kind of functionality I still want to keep, because this gives you very granular control of your vertices in your shader. Very granular. Because if you're using just the model matrix, you can't just change the scale, or you can't change the rotation or anything else. Doing it this way, like that, this actually might be really great for particles, in my opinion. Like this, I might end up using this kind of approach for particle animation, because at this point I have a very fine-tuned control. Like I said, it's very granular control, because I can very easily change my Quaternion rotation. So I can let's say I wanted to add Quaternion rotation based on what do you want to call it? Can't think. I don't know. Based on noise, sorry. But I had like a brain fart. I couldn't think. So, like I say, I want to use scale or rotation based on noise. So I can pass in like the default rotation that I kind of want to apply to it. Then maybe do some kind of weird scaling factor to it. Maybe I can apply scale and my Quaternion values and then use it. I don't know. Like I said, you can, with the granular control, you can do a lot more things. Like, if I were to bring in my model matrix, and let's say I want to modify the scale in real time based on noise, I can't do that, because scale is part of my model matrix. I can't change it. It's part of it. It's no longer a piece of it that I can modify. It's stuck in there. This way, I can take the scale value, multiply it by some kind of noise value, then take that and multiply it by position. So now I'm scaling it. And you might like, why? Like I said, this might be great for particle effects. Maybe you're doing some weird terrain thing. So you can do, like I said, you can do a lot of these things right off the bat, really pretty easily. So yeah, like that's the only thing I can come up with is like this might work really well for particle effects. So this you have more control over scale, rotation, and position that way. So you're not stuck dealing with just the model matrix. So yeah, that's it. There's not really much else to it. I just want to say think. Oh, I guess yeah. So and this is the end result. Like I already showed it to you. I don't know if you care. Like all the code's on GitHub. There's nothing really new to this. Like I said, this still functions the same way. I still create a transform. I still create entities, and then I use before I use the hierarchy. Now it's the transform node, and it's called add function. I say here's the parent, here's the child, and it creates the link between the two, and that's it. So like I said, the new code really works similar to the last code. It's really the transform that has changed quite a bit. And, instead of using the underscore or whatever, now it's all perfect, and that's it. If I were to, let's say, remove the parent-child link, if I refresh, as you can see, they're no longer parent-child related together. Do it again, and they're back. So that is pure transforms. You could go straight from your code, straight to your shaders. You don't even need a model matrix whatsoever. Now, I was kind of hoping I could use this for skinning. It doesn't work. I tried my best to try to get it to work with skinning. I can't get pure transform working with skinning, so I'm stuck using dual quaternions. I think I might be doing something wrong, but I'm pretty sure you probably could. It's just probably very difficult to get it just right. Because of skinning, you have to deal with weights, and applying those weights into all these little pieces and then trying to combine them again, it just didn't work very well. Everything just kept falling apart. So it's very difficult to do pure transforms when you're dealing with weighted bones. So like if a single vertice has 3 bones, I have to compare every piece by 3, and then weight them, then combine them, and then somehow it just didn't work. It just couldn't function correctly. Maybe down the line I might try again. I even contacted Gaber on Twitter and asked them, like, is it even possible to do it? And he's like, I think he told me there's no easy way. He's just stick with matrices when you're dealing with things like that. But like I said, I'm using dual quaternion, so I have less data when I'm dealing with it. So not bad. So this is nice. Like I said, this is a nice arsenal to have. This is nice to know. Pure transforms. Like I said, this might be more efficient for particles. And whenever I get back to working on my particle system, this might be one of the main parts of revamping it. But like I said, it's good to know. It really gets you to really get down to the nitty-gritties of the math of actually how transforms work. So now you have, like I said, you have a very good idea of how the matrix works. The matrix does this. And I think that's the reason why I said matrix, because I think there's an issue. The reason why he wrote this article is because when you're dealing purely with matrices, there's a weird scaling thing that happens. And that's why Unreal Engine does it this way, because that weird scaling happens when you do certain things. I think he shows some videos of like the weird scaling that happens. Unity uses the way we were doing it before, combining matrices, and that weird scaling happens in Unity. But in Unreal Engine, it doesn't happen because they do theirs differently. And this is why this is one of the part of the articles that mentions. Because I remember watching him on Twitter, he was trying to fix these scaling issues in Unity, and that's what he found out by the sounds of it. So it's a great article. I have this linked at the end of the description. All the code is on GitHub. Like I said, this is a great thing to know. He has lots more code for it. So how to combine them, how to use transformed as like a matrix, kind of like how to combine the data. Like setters, like how to create a setter for a transform and things like that. It's tons and tons of code. This guy is great. There's tons of code here. But for what I needed to do, this was more than plenty to get me started and just get rolling with it. So as long as I know the operations, I'm able to kind of use it really fairly well. So again, that's it. That's the end of the video. How long has it been? 30 minutes. I try to see if I can get this down to 15 minutes or 20, but I guess too much talking. So the usual BS, like and subscribe. I want to be sincere. I want to thank you all my Patreons. Not a lot, but I appreciate everything. So I see you guys in the next video, which I'm going to actually continue with this. And the whole reason why transform nodes was created to begin with. There's a very good reason why transform nodes was created. Was because I'm for the next video, which is going to be something fun for me anyway. So I'll see you guys in the next video.